हेलो दोस्तों, आज हम सॉल्व करेंगे अ न्यूमेरिकल ऑन व्हीचर सिस्टम बेस्ड ऑन पीएच चार्ट। तो चलिए स्टार्ट करते हैं। अ सिंपल अमोनिया वेपर कंप्रेशन सिस्टम हैज compressor with piston displacement of 2 meter cube per minute, a condenser pressure of 12 bar and evaporator pressure of 2.5 bar. The liquid is subcooled to 20 degrees Celsius by soldering the liquid line to suction line. The temperature of vapor leaving the compressor is 100 degrees Celsius. Heat rejected to compressor cooling water is 5000 kilojoule per hour and volumetric efficiency of compressor is 0.8. So here we have to use pH chart, and what we have to find out: mass flow rate of refrigerant, capacity of the system, indicated power and COP of the system. So first of all we will note down what is given in the numerical. So what is given? Ammonia is the refrigerant that is given to us. So we have to use pH chart for ammonia. Okay. Next, the piston displacement of 2 meter cube per minute is given. So I will indicate it that Vs, piston displacement Vs. Okay. It is also called as swept volume. So Vs equal to 2 meter cube per minute. Then we have given condenser pressure. Condenser pressure means what? It is discharge pressure. In VCR system we have two pressures, one is suction pressure and another discharge pressure. So condenser pressure means discharge pressure. So I'll write that as PD equal to 12 bar. Evaporator pressure, which is also called as suction pressure, so I'll indicate that as PS. So it is equal to 2.5 bar. So PS equal to 2.5 bar. Then the liquid is subcooled to 20 degrees Celsius by soldering the liquid line to suction line. So I will indicate that point as T3. On our pH chart, that point is 3 point. So I'll note down the T3 temperature as 20 degrees Celsius. So if I convert that into Kelvin, it comes out to be equal to 293 Kelvin. Next, the temperature of vapor leaving the compressor is 100 degrees Celsius. Leaving the compressor means it is point number 2 in our pH chart. So corresponding to that point, our temperature given as 100 degrees Celsius. So convert it into Kelvin, it comes out to be equal to 373 Kelvin. Next, volumetric efficiency is given 0.8. So I'll note down this as 0.8. And next, heat rejected to the compressor cooling water is given, that is 5000 kilojoule per hour. So that is what the data given to us. And what we have to find out: mass flow rate of the refrigerant, COP of the system, indicated power and capacity of the system. So these are the four terms that we have to find out. Okay. So let us proceed with the problem solving now. First of all, we have to go for the pH chart, that is ammonia pH chart. So this is what I have, pH chart for the ammonia, right? And we have given suction pressure and discharge pressure. So first of all, I have to locate or draw two horizontal lines indicating suction pressure and discharge pressure. So we have given suction pressure as 2.5. So this is the line of 2.5 pressure bar, and this is the line of 12 bar pressure, that is discharge pressure. So I'll draw two horizontal lines like this and like this, which are suction pressure and discharge pressure. Okay. Now here I have to locate the point number 1, 2, 3, 4. That is inlet to the compressor 1 point, exit of the compressor 2 point, exit of condenser 3 point, and exit of expansion valve or entry to the evaporator, that is 4 point. So these are all 4 points we have to locate on the pH chart here, right? Now we know that the compressor exit temperature is given to us, that is 100 degrees Celsius. Okay. So that point would be on the discharge pressure line because that is after the compression, right? So that is given 100 degrees Celsius. So if you see here, these temperature lines are going like this. These are temperature lines, 10 degrees Celsius, 20 degrees Celsius, like this. So we have given temperature of 100 degrees Celsius after compression. So this is what 100 degrees Celsius line. So if I go vertically upward following this constant temperature 100 degrees Celsius line, it touches to the discharge pressure lines at this point. So that is what our point number 2. Now we know that the compression is isentropic compression. So to locate the point number 1 this side on the suction line, we have to go we have to follow constant entropy lines. So these are constant entropy lines. Okay, so we have to follow constant entropy lines from this point to this side up to this discharge suction pressure line. Okay, so that line is nothing but this one. So here is 100 degree Celsius point, and from that I am drawing a line indicating compression process from 1 to 2. Now after that, this is what the condenser line or condensation line up to this point. Okay, but now it is given in the problem that the condensation occurs up to 20 degrees Celsius. So we have to follow up to this 20 degrees Celsius line. Okay, that means this is what my line of condensation up to 20 degrees Celsius line, right? Then follow vertical line from here, which indicates the isenthalpic expansion process, means enthalpy remains constant. And in pH diagram we have enthalpy on x-axis. So vertical line indicates constant enthalpy line. From there, draw a horizontal line which indicates the evaporator process, that is 4 to 1. Okay, like this. Now this is what our point number 1, point number 2, point number 3 and point number 4. This 3 dash point is on saturated line. The line cutting constant pressure line and saturated line is nothing but 3 dash point. And here also in this side we have 2 dash point. Okay. Now in Vapour system we have to find out enthalpy at each and every point. So corresponding to all these points 1, 2, 3 and 4, we have to note down what is the enthalpy. So corresponding to this one point, the enthalpy is equal to 1428 kilojoule per kg. So if you see here, if I draw vertical line from this one point downward, I have a value specific enthalpy corresponding to that one point. So it is near to the 1400 line, right? So I will take the value as 1428. So you can take that accordingly. You can take 1430 also, you can take 1432 also. It's depend on you how approximately you take the value. Next, corresponding to this 2 point, that is after compression process, so it is near to the 1600, so I'll take that as 1630 kilojoule per kg. That is enthalpy corresponding to 2 point after compression. Next, corresponding to this 3 point and 4 point, because both are same, because the 3 to 4 line is isenthalpic line, so enthalpy of 3 and 4 is same. So it is equal near to the 270 kilojoule per kg. So in between 200 and 300, so I'll take that as the 270 kilojoule per kg, right? Now we require this temperature also, that is temperature corresponding to 1 point. That is not given in the problem. We just drawn this constant entropy line following this constant entropy line, and we intersect at suction pressure lines at this point. So corresponding to this point we have to note down the temperature. So if you notice here, this point is of minus 10 degrees Celsius and this point is of minus 20 degrees Celsius, right? And corresponding to this point, if I find out the temperature, it comes out to be equal to minus 14 degrees Celsius. So if I convert that, we will get 259 Kelvin as a temperature. Along with this one, we have to find out what is the specific volume of this one point, that is specific volume of refrigerant at the entry to the compressor. So corresponding to this one point, specific volume we have to find out. So how to find out that? If you see here, this line is of specific volume line. This one is also, this one and this one. So these lines are specific volume lines. So this line is of 0.5. This line becomes the 0.45. My one point is near to the 0.45. But just before that, it is not exactly equal to 0.45. So I'll take that as 0.47 meter cube per kg. Okay, 0.47 meter cube per kg, I'll take that value. So that is V1 equal to specific volume, V1 equal to 0.47 meter cube per kg. Along with that, we have to find out the temperature of 2 dash, and that is nothing but temperature of 3 dash, because in saturation dome the temperature of horizontal line remains same. So that is equal to 30 degrees Celsius. So if you see here, this is of 30 degrees Celsius line. So from here, this is nothing but the 30 degrees Celsius line. So this is what T2 dash, T3 dash, and it is equal to 30 degrees Celsius. So if I convert that into Kelvin, it is equal to 303 Kelvin. Okay. So now we have all the values that we have taken from the psychrometry chart, and let us now proceed with the solution. Now, what is first of all we have to find out? I will write first of all what are the values that we have taken from the pH chart. So first of all, the temperature, T1 temperature we got, T1 equal to, and that is also equal to T4. Okay, so it is equal to minus 14 degrees Celsius, which is equal to 259 Kelvin. Next we got temperature of 2 dash point also, which is also equal to temperature of 3 dash point also, right? So that is equal to 30 degrees Celsius. So if I convert that into Kelvin, it is equal to 303 Kelvin. Next, specific volume of point number 1. So I'll write that as VS1. So it is 0.47 meter cube per kg. Next, enthalpy corresponding to 1 point. So we got that as 1428 kilojoule per kg. H2, enthalpy corresponding to 2 point. So it comes out to be equal to 1630 kilojoule per kg. Next, finally we have H3, which is also equal to H4, that is equal to 270 kilojoule per kg. Right. So this is what the data that we got from the pH chart of ammonia. Now let us go for the solution one by one. So first of all, we have to find out the mass flow rate. Mass flow rate. So I will indicate that as m.1, mass flow rate at the entry of compressor. Okay. So how to find out that? What the value we have? In the problem we have given volumetric efficiency. So what is that volumetric efficiency? How we can write that? So volumetric efficiency equal to VA upon Vs. Actual volume divided by swept volume. Actual volume taken by the compressor divided by what is the swept volume. Okay, so that is nothing but the volumetric efficiency. How do we write that? Actual volume. So we can write that as mass flow rate into specific volume of refrigerant corresponding to 1 point divided by Vs. Okay. Now from this one we have to find out the m.1, that is mass flow rate, because we have this swept volume given in the problem. m.1 that we have to find out. Vs1 just we got from the pH chart, and volumetric efficiency given in the problem again. So I will write that for m.1. So the which is equal to Vs into volumetric efficiency divided by Vs1. Okay. So this is equal to Vs. How much it is? It is given by problem. In the problem it is given. So it is 2 multiplied by volumetric efficiency 0.8. Okay. So divided by Vs1. How much it is? 0.47. That we got from the pH chart. So if I solve this, I will get mass flow rate of the refrigerant as 3.404 kg per minute. 3.404 kg per minute. Next, what we have to find out? We have to find out the capacity now. Capacity of the system. Capacity of system. Okay. Now, refrigerating effect per kg of refrigerant, that we can find out, right? So I'll write refrigerating effect per kg of refrigerant. Okay, that we have to find out first. What is that? That is equal to H1 minus H4. It is equal to H1 minus H4. That is refrigerating effect per kg of refrigerant. 1 kg refrigerant, how much it can absorb from the substances. That is what the refrigerating effect per kg of refrigerant. So it is H1 minus H4. So what is H1? 1428 minus what is H4? It is equal to 270, which is equal to 1158 kilojoule per kg. Okay, but now we have to find out the capacity. So we have to multiply this by mass flow rate. How much is the mass flow rate? It is 3.404 kg per minute. So whatever the value we got, it is per kg. So how much kg we have? 3.404 kg per minute. So total refrigerating effect now. So total refrigerating effect. What is that? It is equal to m.1 into refrigerating effect per kg. Okay. So put the values 3.404 into 1158. Okay. So put those values and find the value. So it comes up to be equal to 3941.83 kilojoule per minute. Kilojoule per minute. So that is what the total refrigerating effect. Now if I divide this by 210, because 1 ton of refrigeration is equal to 210 kilojoule per minute. So I'll write that also here. We know that 1 TR, 1 ton of refrigeration is equal to 210 kilojoule per minute. Okay. So now we have to find out capacity of the system. So if I divide this value, total refrigerating effect, by 210, I'll get total capacity of the system in ton of refrigeration, right? So total capacity of system equal to how much it is? 3941.83 divided by 210. So that value is equal to 18.77 TR, ton of refrigeration. So capacity of the VCR system is how much? 18.77 ton of refrigeration. Now next point, what is that? Indicated power. Indicated power. Indicated power. So now indicated power means what? How much amount of work is consumed by the compressor. Okay, how much amount of work consumed by the compressor. So I'll note down that as WC. Okay, what is that? m.1, that is mass flow rate of the refrigerant which is taken by the compressor, into enthalpy difference during the compression process. So H2 minus H1. H2 minus H1. So this is equal to 3.404 into H2 is given. What is that? 1630 minus 1428. Okay, H1 is 1428. So this value is equal to 687.61 kilojoule per minute. Okay, so the work of compression is equal to 687.61 kilojoule per minute. But now in the problem we have given that the heat is rejected to the compressor cooling water. Heat is rejected to compressor cooling water. मतलब क्या? To cool the compressor, the heat is released by the compressor to cool the water circulated through to cool the compressor. Okay, That is nothing but some amount of energy is required to cool the compressor. Okay, so that is nothing but, what is that? Heat rejected to compressor cooling water. ओके, हीट रिजेक्टेड टू कंप्रेसर कूलिंग वाटर, मतलब जो भी कूलिंग वाटर है टू कूल द कंप्रेसर जो यूज करते हैं हम लोग वाटर, उसको भी रिजेक्ट कर रहा है कंप्रेसर उसका हीट. सो दैट इज आल्सो हीट वी हैव टू टेक इनटू अकाउंट, राइट. सो हाउ मच इट इज गिवन इन द प्रॉब्लम, इट इज गिवन 5000 किलोजूल पर आवर. So it is per hour. So per minute अगर मैं इसको निकालूंगा, so that is equal to 83.33 kilojoule per minute. So that is given in the problem. So what would be the total work done? So total work done would be equal to what? That WC plus this heat rejected, right? Heat rejected. So it is equal to what? 687.61 plus 83.33. So which is equal to 770.94 kilojoule per minute. अगर ये टोटल वर्क डन समझ में नहीं आ रहा हो तो फिर से उसको समझ लेते हैं. सो जो भी वो वर्क कंज्यूम करेगा कंप्रेसर, वो दो तरीके से यूटिलाइज करेगा. एक रेफ्रिजरेंट को कंप्रेस करने के लिए, और दूसरा जो भी कूलिंग वाटर यूज करेंगे टू कूल द कंप्रेसर, उसको वो हीट रिजेक्ट करेगा, राइट. सो टोटल कंज्यूम विल बी द वर्क required to compress the refrigerant, and another one the energy given to the refrigerant. So that's why the total work done by the work consumed by the compressor. So here it should be actually total work consumed. Consumed work by compressor. So total work consumed by the compressor utilized for two reasons. One is for compressing the refrigerant. So WC is nothing but required work to compress the refrigerant. And another part of that consumed compressor work is utilized to reject the heat to the cooling water, just to cool the compressor. So जो भी cooling water use करेंगे, that is used to cool the compressor. तो वो कुछ ना कुछ heat वो absorb कर लेगा from the compressor. So that is what that part. So total work consumed by the compressor would be equal to work of compressor to compress the refrigerant, and another one is heat rejected to the cooling water. Okay, so that is what total 770.94 kilojoule per minute. Next, finally, what we have to find out now? Finally, that is COP, fourth one. COP. What is that? It is nothing but total refrigerating effect divided by total work of compression. Okay, total refrigerating effect divided by total work of compression. So total refrigerating effect हम लोगों ने निकाला है, it is equal to 3941.83. So divided by 770.94, that is total work of compression. So if I find this value, it comes out to be equal to 5.11. So this way we can find the COP. Okay, so if you see total refrigerating effect, it is 3941, and total work of compression, it is 770.94. So those values we have calculated in previous slide. So those are here. So total work of compression is this one, 770.94, and the total refrigerating effect, so that is equal to 3941.83. So this is what total refrigerating effect. So we have to use those values to find out the COP. So finally we got COP as 5.1. Okay, so this way we can solve the VCR problem based on pH chart. Thank you.